Robots with their own nervous systems? How is that possible? It sounds like sci-fi, but Harvard researchers have made it into a reality. Neurobots are remarkable creations built entirely from frog embryonic cells, but go far beyond earlier biohybrid machines that could only move in simple ways. So how did researchers do it? Well, to form a nervous system, the researchers introduced neural precursor cells early in development, allowing them to grow into fully connected neurons inside the bots. These neurons self-organize into active networks, giving neurobots a form of internal control over their movement and behavior. This results in more complex motion, new elongated shapes, and far more dynamic activity than their simpler predecessors. Even more astounding, researchers observed changes in gene expression, including activity linked to visual system development. This breakthrough opens up an exciting new frontier in biomedical research, offering the potential to solve medical challenges that have yet to be imagined. And if you need a reliable component to solve challenges in your design, there's only one place to go, and that's Mouser Electronics. ABB Eden safety sensors are non-contact safety devices designed for door interlocking and safe position monitoring in industrial systems. Their non-contact operation eliminates mechanical wear, while high sensing tolerance improves resistance to vibration and reduces unwanted downtime. With IP67, IP69K sealing, and optional coated electronics, they perform reliably in harsh environments. Their compact design and possible 360-degree mounting simplify installation. Features like LED status indication, series connection with PLE, and M2 connectors help enhance usability and reduce system complexity. Operating from a wide temperature range, ABB Eden non-contact safety sensors are ideal for demanding applications, including industrial control, food processing environments, and more. Check them out today by visiting Mouser.com or by clicking the link below. Potentiometers are variable resistors that adjust voltage or signal levels via a movable contact. But how do they work? To help explain, we present David's Corner.
Thanks, Andy. In automation systems these days, most of the processes bring in information from sensors and they send it out through actuators. There's very little human involvement needed, but we still see plenty of operator pedestals and panels where there's push buttons, things like this, to be able to allow the users to set parameters, start and stop operations. But there's one type of device that's a little bit trickier as to how it works, and this device is a potentiometer. When we see these devices sticking out of a panel, they might look a lot like a push button or a simple selector switch, but if we operate them, we find that they turn smoothly from one position to another, almost a full circle. Well, what's happening inside is there's a ring of resistance, and as we move the potentiometer, the resistance increases. That resistance increase creates a voltage drop between two terminals, a reference point and ground, and that voltage can be read by an analog input on a PLC. Well, that's a little different than the digital inputs that we use for push buttons and selector switches, but these analog inputs are great for setting most typically the speed of a simple running motor when we don't need a complex control system to run it. Sometimes we even find these right on the front of a variable frequency drive for local potentiometer control. So we don't run across them a whole lot, but they're a very useful device when what we need is precise control over the speed of a system. Andy, back to you.
Thank you, David. All right, it's time to adjust your knowledge gains in our Smart Bit quiz with our 3 control automation questions. The questions are scored using actuator output percentage, and today we'll be testing your knowledge on Neurobots. Let's begin with our first question for 25%. The Neurobots' co-evolving morphology and control must fundamentally violate which classical control assumption? Is it A, time invariant plant dynamics, or B, observability of system states? And the answer is A. time invariant plant dynamics. The plant itself is changing over time, breaking the assumption of fixed system dynamics. Okay, let's move on to our next question worth 25%. Neurorobot dynamics are most rigorously captured using A. State space LTI models, or B. Koopman operator theory. And the answer is B. Koopman operator theory. Koopman operators lift nonlinear evolving dynamics into a higher dimensional linear framework. Okay, let's go to our final question worth 50%. Gene expression altering system behavior over time is analogous to A. Fast disturbance rejection, or B. Slow manifold evolution. And the answer is B. Slow manifold evolution. The system evolves along slow changing internal dynamics. Want to try again? Just click the link on your screen and be sure to check out our other Automator Edge videos for the latest in control automation.